Say that again, Tabitha?
That line got evacuated because it smelled.
Like what?
It smelled like gas.
Like natural gas?
It smelled like gas.
Oh,
Like
interesting.
propane, yeah, like.
Oh, interesting.
Were you in there too, right?
No.
Was it this building?
I was in the same building, no, it's.
Did I make you guys sit through natural gas?
Grandview.
And then I came
Sorry
to
if
this
I
building
did.
that smelled
Yeah, I
terrible.
didn't go, it was something nasty, it was just a porta potty that was sitting right next to an air vent.
Well, there is a problem. Sean has wicked
I'm not going
allergies,
that
so I don't smell anything. If you're leaking, I don't know, methane in here, I wouldn't know. You have a fleet of cows back there spewing methane, I wouldn't even notice. So,
Your nose is purely decorative. All right.
say it again.
Your nose is purely decorative.
If you call this a decoration.
You seem to be proud of it.
I
so
call
it's
it,
like a
proud of it, I
decoration.
just talk about it like it's so
It's
obnoxious.
decoration.
I don't know.
Purely decorative.
Yes,
No.
we'll call it decoration. It's
Your
something.
nose.
It's something.
Like,
All right, so last time we were talking about wonderful things called probability distributions. Remind me what those are and why we care about them. Why do we care about probability distributions? Why do we care about these things? Or what are they? Forget the why we care. We'll come back to why we care. What are they? What do they look like? What do they contain? Be brave, my friends.
The random variable and the probability.
Beautiful. What do they look like? That's perfect exactly. We have a variable, we have a random variable. We got a random variable. And we've got probabilities of each value of the random variable. What do they generally look like? At least how we've been looking at them so far. The one or two. Say that again.
The probabilities of.
Nice. So in general, example number one, the one you're talking about, Tabitha, is the example number one, which was rolling a single die. Rolling a single die.
You weren't here. How the heck did you know that? I just looked at my notes. Your notes. Where's my notes?
And that single die distribution, let me swing this over to the side, make sure we can see it. That single die distribution contained the random variable column x, which was the number of pips. And then the probability column over here, p of x. This guy right here talked about what could happen if we actually rolled a single die. What could happen if we actually rolled a single die?
6 different possibilities.
Exactly. 1, 2, 3, 4, 5, and 6. And then the likelihoods of each of those outcomes to the right of it. Which, as Tabitha said, 1, 6, they're all the same. 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Now the reason, this was a very specific kind of probability distribution. Do you remember what I called this when all the probabilities are the same, what kind of distribution it is? It starts with a U.
Oh, yeah.
Perfect. It was a uniform distribution. They're not all uniform. They're not all. There's a very small subset of all the distributions that are uniform. But this is definitely one of them. Flipping a coin is also a uniform probability distribution. If you call heads 1 and tails 0. And I loved what Jess said too about the idea you could treat this as qualitative data by calling these colors instead of 1 through 6, call them green through dark green or something like that. But if we assign numerical value to them, they are quantitative. They are quantitative. In general, however, a probability distribution on discrete variables, more on that difference in about a week and a half, is going to look something like this, where you've got a t-table. You've got a t-table where your random variable is defined in the left column, right? And the probabilities of those random variables are in the right column. And these are going to be filled up with values. You're going to have a probability for every random variable value. These are all going to be spelled out for us. And these are going to change as we go through today. I've got a few, 3 or 4 different distributions I want to look at today. And I guess the real big reason is that's what they are. That's how they look. That's what they contain. Why do we care about them? What did we do with this once we had it? Once we had this, the very last thing we did with this distribution, I asked you a question. And it involved this Greek letter. Remember that guy?
Oh, yeah.
What is that guy? It's mu, very nice. And what does he stand for in this class?
Average of
The population average.
Beautiful, beautiful. It's the population average. Why am I calling this, all of a sudden I got an average, they're calling it a population average. How can I legitimately call this a population average? We've been talking about sample averages all this time, right? X bar, X bar, X bar, X bar. All of a sudden I change it to mu and say it's a population. Why? Why? If it was a population, what would that imply about this?
100%.
That everything I could possibly see is contained in this table. Well, isn't everything I could possibly see contained in this table?
For a six-sided die.
For a exactly, for this experiment, for a six-sided die, yes, absolutely. Everything's contained in here, and didn't we drive that point home by adding up these probabilities last time?
Yes.
And saying that it was equal to 100%?
Yep.
Which means everything that could possibly happen is disjointedly listed out here. So I got no problem calling this mu and saying that the average roll on a six-sided die was what? Remember what it was?
3.5.
3.5?
Yep.
3.5 was our average? Did that upset anybody? It was 3.5. Maybe a little bit. I think we discussed this a little bit because we can't actually roll at 3.5.
No.
So does 3.5 upset you? Okay, we got a couple yeses and a couple nos. Those of you that are saying no, why doesn't it upset you that it's 3.5? Be brave. Why doesn't it upset you?
Average is at one roll.
An average is what?
All of the rolls.
Nice! Kelsey, beautifully said. An average is not one roll. An average is not one roll. An average is the typical result over all the rolls. So in other words, Kelsey, somewhere I'm going to roll a 6. And somebody else is going to roll a what? A 1. And those two people together rolled a sum of 7, which means each person rolled 3.5 on average. Somewhere, somebody's going to roll a 2, and somewhere else somebody's going to roll a 5, and on average, those things are going to average out to 3.5 per roll, and same with 3 and 4. And the reason I can say that is because of what Beth said about 5 minutes ago. These are all the same. So just as often as I roll a 6, somebody else is going to roll a 1 with the exact same frequency. So the number of 6s and the number of 1s cancel, if you will, to 3.5, and 2 and 5, and 3 and 4. And it all works out to 3.5 at the end. Perfect. Beautiful. Beautiful. Makes sense? Believable? Kind of remember. I remember that from last time. Yeah, that's good. Good. Now, let's go back into this again and change the experiment now. The very last thing I had you guys do last time was roll 2 dice. This is going to be experiment number 2. I'm going to show you your results here. Let me turn this bad boy back on. Switch over to here, go to this, it should pop up. Yay, technology gonna work for me. It was just working, wasn't it? Blank screen. Blank screen.
There you go.
Turn it off, turn it back on again, just like Microsoft product. Good. All right, so I'm gonna go edit. Here are our results. Okay, I'm gonna do this. I'm gonna put alpha L. Oh, I can't do that. Maybe I have to go alpha list. Yeah, I gotta do this. List L, will this work? Yes, it will. Yep, let me delete this list now. There you guys go, right there. Here's your results. We kind of started this distribution in class yesterday. So, here's experiment number 2. Experiment number 2. Take a look at the screen so you guys can see your results if you're watching this later. Kill the light so you can actually see that. Now we're going to roll 2 dice. 2 dice. Just like you guys did yesterday. Okay, and I want to create the distribution for 2 dice. And when you roll a pair of dice, what are you most likely interested in? Do you play a board game with your 2 dice? What are you most likely interested in on the 2 dice? Doubles, so in other words, looking at both dice faces facing up at you.
Yeah.
So doubles when you get a jail-free card on Monopoly, for example. Yes, very nice. Or you're playing craps, and you don't want to get doubles off the bat, because that's snake eyes, and you crap out, you lose your bet.
So we want the face side up, that's what we're doing.
You want the face sides up, exactly. And in particular, usually you want the sum. Because like in craps, for example, you're betting on the sum, the 8, the 6, the 12, whatever it is. So we're going to define the random variable, and this is just how we're choosing to define this to match what you guys did yesterday. You might want to make a new distribution where you're interested in the doubles. And we can come back to that at a later date. I mean, there's all kinds of ways to define what you're interested in. Maybe you're interested in the number of ways the number 2 can come up on a pair of dice, which would only be 3 outcomes. You might not get any 2s, you might get 1 2, and you might get 2 2s, which would be doubles. So, but right now, to keep it simple and start, so we can mess with this all day long and all term long, and we will continue to do that. But to keep it simple, let's just define our random variable to be the sum on the 2 dice. And then we'll do the probabilities over here. Okay, let me swing this down. Over here. There we go. Very nice. And I think we had this contained already, didn't we? We had this yesterday. We had figured this column out yesterday. 2, 3, 4, up to what?
12.
Yeah. That was perfect.
The numbers?
Say that again? No, I got them up here. What I want you to do is I want you to look at them.
Okay.
Because this is experimental data. This is experimental data. Boom, boom, boom. What's going on as we scroll through these probabilities? Or they're not even probabilities yet. Right now they're just frequencies, aren't they? They're just frequencies. But what do you notice about them? Do you think this is one of those uniform distributions Beth mentioned earlier? Do you think it's uniform? So do you think all these probabilities should be the same based on the results you guys saw up there? What do you think? Kelsey's saying no, Beth's shaking her head no back there, Mike's shaking his head no, Travis is saying no. No, we got a whole bunch of saying no. What's making you think it's no?
Because they don't have the same frequency.
You would think if these were uniform probabilities, those frequencies would be a little bit closer together. But as it is, what appears to be happening with the frequencies as we cycle through them?
L-shaped, yeah.
Maybe we get, actually somebody had called that last class, if I remember correctly, bell
I
shapes.
was just saying it was a bell shape and that the frequencies in the center happen more often because there's more possibilities of rolling that way.
Okay. First of all, I want to take a look. I love this. I love this. I love this. Give me 30 seconds on that if you don't mind, Athena. I want to real quick turn a stat plot on my L5 and L6, just because that's where I stuck my data. L5 is these, and L6 are the frequencies that we're going to have to morph a little bit to get these numbers. So we'll come back to that. I promise. I promise. Okay. And I'm going to make it a line plot just to mix it up a little bit. Got nothing turned on. Zoom 9. Oops. Got to turn them on. There we go. Zoom 9. Invalid dim.
Because you turned on L1 and I put here.
Oh, did I forget to change the plot? Oh, it's L2. That should be L6. Sorry.
You gotta pick the right.
I do. There. That definitely doesn't look uniform.
Oh, no.
Uniform would be straight across here somewhere, right?
No,
But it's-
that's uniform, definitely.
There's definitely uniform. We could test it. We could test to see how likely it would be. And with a small sample, Lucas, you could have that kind of, it's interesting. I just got an email this morning speaking of a slightly tangential topic. A former 243 student about two and a half years ago sent me an email from Spain, listening to her iPod. 449 songs on it. 5 of which were Keisha, 28 of which were John Mayer. And while she was listening to her shuffle, she got 6 songs in a row, Keisha Mayer, Keisha Mayer, Keisha Mayer. And she said, what's the chance of that happening? And she had used this project's ideas to come up with two numbers of the idea of probability. And my first question was, why did you have Keisha on your iPod at all? My first question. My second response was, hell yeah, sister. That was so rad what you did, because what she did was she did this without replacement idea that you guys did. But she applied it from, what's the chance I turn my iPod on and play 6 songs and get Keisha, John Mayer, Keisha, John Mayer, Keisha, John Mayer. That's like saying, what's the chance I pick a coin up and flip it 6 times and get 6 heads in a row? You'd think something was up, wouldn't you? But what if I gave you 200 flips? Would you think something was up if I gave you 200 flips and you flipped 6 heads in a row somewhere? No, you wouldn't, because what does randomness do? It tends to clump. And what I just did, it tends to clump. Now, it's less obvious in that, but she has 449 shots, if you will, to get those 6 songs together. It's nowhere near as high as getting, say, 6 heads in a row out of 200 flips, but it's still right in there. So the point is, this could be uniform. It could follow that distribution, but it's most likely not to follow that distribution. See what I'm getting at there, Lucas? Good. Very good, very good, very good. So now, the question is, what distribution does it follow? We have vote for bell curve. Let's figure this out. Rather than trying to, because our data set was fairly small, this is still a fairly small data set, even with a couple hundred data points. Let's see if we can figure out what these are supposed to be from the ground up. For example, what's the chance of getting snake eyes? What do you think? Something out of something.
It's 1 out of...
Let's say you gotta time it.
Good. Okay, I love this. Use this project. Use the ideas from this project.
6 times 6 times 6 times 6 times.
Well, that would be 6 dice. Just 2 dice.
Oh, 2 to 6 times. 6 to 2?
6. We have 2 votes. We got 2 to the 6 and 6 squared.
6 squares.
Why 6 squared? That should be our sample space. What I'm hearing here is the sample space for this experiment. The sample space for this experiment should be 6 squared. I love that. Why do I love that? Because it's 6 times 6. Why does 6 times 6 make sense?
Because there's 6 sides on both dice.
There's 6 sides on one die and then 6 sides on the other die. So that means there's 36 possible outcomes for the 2 dice. I love that. Just like there was just 6 outcomes for 1, every time you add another die, you add 6 times more possibilities for getting the job done. So I love it, 36.
136.
And for snake eyes, there's only 1 in 36. Of all 36 of those, there's only one way to get snake eyes. Get a 1 and get a 1. That's what you have to do. You have to get 1 on both. So there's only 1 chance out of 36. Believable?
Same with 12.
Oh, I have a vote. Wouldn't that be the same with 12?
Mm-hmm.
Because to get 12, you have to get 6 and 6. There's no other way to get 12. So I like this. We're building it from both ends. That's good. So you got 1 in 36 and 1 in 36. So that's 1/18th out of the way. Let's build the rest of it. How about getting 3?
So you would have to get a 2 and a 1, right?
Yes.
But then you could also get
Or 1 and 2.
a 1 and a 2.
Okay, I love this, and I love the fact you guys caught it so quickly. Hang tight. This is going to help us right here. This is going to help us right here. We're going to switch back over to here. We're going to open the Google.
The Google.
The Google. Okay, we're going to talk. What should we Google here? We should Google outcomes for rolling pair of dice.
Like the old times table charts. You go and then you can.
Hot damn, look at this. Yeah, it's exactly like that, Athena. Thank you for bringing that up. Hang on, let's get there. There we go. It's a shift. Oh, is it plus? How do I get the screen? Oh, there we go.
Right. And you got this.
Look at this. Here's your, you see your 36?
Yeah.
You see your 36? You got 6 outcomes across the top. Let me slide this forward. Let's see what's going on over here. There we go. It's essentially a times table chart. It's exactly what it is. Except instead of multiplying to get the cells, you're just putting them together. So Athena's remembering this. I remember learning times tables this way too. You had your multiplication, 1, 2, 3, 4, 5, 6, 7, 1, 2, 5, and then in the cells you put the product of those numbers. Here you're not putting the product, you're just putting the dice next to each other.
That's amazing.
So it's pretty cool, huh? It's pretty cool. It's unfortunately a little bit limited too. If you had a 3rd die, which we'll see here momentarily, you'd have to actually bring this thing into 3 dimensions to have a 3rd die, which is very cool. Very, very cool, but a little hard to see 2-dimensionally. But that's okay. We'll get that when we get to it. So do you see your snake eyes? It's right up here. Do you see your 3s?
Yes.
There's 2 different ways.
They occur twice.
It has to occur twice. Now, some of you might be saying, wait a minute. If snake eyes was 1 and 1, and 3 is 1 and 2, why are there twice as many ways to get 3 as there are to get 2? What makes that difference there? Beth? Say that again? But there's 2 dice for snake eyes too, aren't there? Ah, think about the 2 different colors.
Yep.
To get 3, you can get 2 red, 1 green, or 2 green, 1 red. That's 2 different outcomes. Snake eyes is 1 green and 1 red. You can't make that be any other way. If you try to turn the dice to make it different, you're going to get the same exact outcome back. So doubles are only going to occur in 1 way. There's your doubles right there, Cassie. Right down that diagonal. They only occur in 1 way each time. But the non-doubles can occur in 2 ways each time. Very nice, my friend. Very nice.
Wouldn't 11 be the same?
Yes, my friend. 11 would be the same right here. There's your 11 diagonal. So that's 2 out of 36. I love the way you guys are building this. No one's ever built it from the ends in before. This is fantastic. Let's put this down so you can see the distribution you guys are building. Beautiful. So want to build 4 and 10 next, friends? Now you can see 4 is kind of cool because how many ways can you get a 4?
1 and 3.
Yeah, 2 and 2.
2 and 2.
And 1 and 3.
And 3 and 1.
So what's cool about that is you have one of the single doubles in there plus the 2 non-doubles on the end. So that's why it's an odd number of 3. And 10's the same way, isn't it?
That's right.
6 and 4. 5 and 5. And 4 and 6.
Okay, so
Tabitha, go. Go.
it clicked.
Good.
The way that this picture is,
Yes.
there's less probabilities on the outside and there's more in the middle because it goes straight across. That's why in the middle of the thing there was nothing.
So happy right now.
Yeah. Bell all around.
I don't even know how to explain.
No, you explained it beautifully. Basically, the diagonals are giving us our sums, aren't they? These diagonals, here's 12, 11, 10, here's 9. The longest diagonal follows which sum?
Smack through the center.
Smack through the center at that guy. That 7 is the longest diagonal. So you got 4 and 36 here, 5 and 36, 6 and 36, and then it starts going back down again until it joins back up with 1 and 36.
I'm going to start going for numbers like that when I'm playing games
Well, you should know this. You should know this. You should know. I mean, here's a lame reason. Here's a lame reason to know it. Here's a lame reason. Years ago on that show, Who Wants to Be a Millionaire, the final question somebody had to ask was, if you roll a pair of dice, what's the most likely sum? And the choices were 6, 7, 8, and 9. And the person picked 8. Now, here's the thing. Here's the thing. Based on the data we collected in class today, first period, at 10:15, the same 243 class, 8 was the most likely outcome in their little sample set of data. For you guys, who's your guys?
Did the person get the $1 million?
No, they got it wrong. They said 8, it should be 7.
Should be 7.
It should be 7. 7 has the highest probability. Wow.
You lost.
I'm not going to get that question.
Well, I guess my definition of loser, that was a loser thing to say, right?
Yeah.
So by 7 is the most likely because it's got the highest probability. It's 1/6. It's
That's
1
when
in
you're
6.
playing dice, 7, a lot of these games are lucky number.
Oh,
Yes,
yeah.
craps, 7 and 11, you win off the bat.
That's why Snake Eyes is
Right? Any craps, 7 or 11,
If
you
you
win off the
get
bat.
that
So there's all,
out.
the number 7 with a pair of dice, I'm telling Cassie, when you're rolling dice, you should know that. You're more likely to roll a sum in the middle than on the ends. I think intuitively we knew this. Part of it's just by growing up with games like craps where Snake Eyes is bad.
Yeah.
But also part of it is when you play these games enough, you begin to realize these numbers do show up more often than not. So here's a question I have for you guys. Is that a bell-shaped distribution of data?
Yes.
It's close. It's not perfectly bell-shaped, but it's arguably bell-shaped. It's actually beautifully pyramidal.
I'd say it's kind of pyramidal.
It's, yeah, pyramidal, if you will. What? Let me show you. It's a real word. It's a real word.
Okay,
Okay,
Mr. Bush.
You're lucky I like you, Raphael. You're lucky I like you. Use the Google. Pyramidal exists. Check this out. Check this out, friends. Stop laughing at him. That wasn't funny. What I've got here is a simulation to show you the pyramidal nature of this distribution. So check this out. Here are your 2 dice down here. Your 2 dice are down here. Die number 1, die number 2. What I'm going to do is I'm going to go ahead and roll this thing. Let's roll it 36 times. Now, what do you notice about those 2 pie charts at the bottom?
They keep on shifting, obviously.
They keep on shifting. Why?
Because the probability of I guess the number of times you roll the die, the probability is going to shift.
Good. And what should these eventually look like?
The same.
They should look the same, and they should both be indicative of this one that's back here behind the screen, eventually, correct?
Yeah.
We looked at it yesterday, the beautiful pie chart that sprinkles out to six equal-sized pieces. But look up top. Now look at that right now. That's messy right now. That doesn't look anything like our distribution, does it?
How many times did you?
36, exactly 36, Tabitha. And the reason I did exactly 36 was I wanted to show you exactly the 36 in the sample space of the denominator over there.
100%.
But that 36 is on average, right? Out of every 36, on average, Beth, what's that wonderful phrase? Over time, on average, we're going to see 1 in 36 2s. And we're going to see 1 in 36 12s. Over time, on average. That is not a guarantee that in 36 we're going to see it. Look, we saw no 12s. We saw no 12s yet. So what do you need to do?
11's way out.
And look at all the 11s. We saw 5 11s where we should see 2. So what I'm going to do is, let's let this thing do its thing.
You're trying to use the
I'm going to try to stapler again. Maybe by the time I actually get to not work, there'll be plenty of trials up there. Let's see what we're trying to see.
Why do you use?
I want to go to walk and point.
I want to walk and point.
Hey, let me now. Hey, let me now.
Oh, it stopped. Good.
It did? No, the graphics, Michael, this is annoying. This is annoying. The graphics, I think it's because I'm pulling this across the campus through the network, it slows down. But they do eventually catch up. Look at these pie charts. What's happening? Exactly. They're identical and they're 6 each, which is what they should be. The 6, because they're following that distribution from back here. And look at the guy up top.
Yeah.
Look at the guy up top. That guy up top is beginning to look, it still looks bellish. I'm with you, Dina. It's definitely, if you think about the actual distribution, you could arguably call it a bell shape. Even though it's not a bell, it's actually a perfect pyramid, or a perfect isosceles triangle, I guess is what it is. But, which means it has isoscelosity, which does not exist. That word doesn't exist. I made that one up years ago. It sounds like a food. It's good. It doesn't really exist, but I think it makes sense. So here's the. Let me get a floss. But here's the deal. Here's the deal. We do now see clearly 7 is the most likely outcome, and it's tailing off to the side here. Here's what I want you guys to do. While we're letting this thing refresh, can you guys give me the average and standard deviation of this bad boy? Find me the average and standard deviation. You know how to do it. Use it like you've been doing it. What have you been using to find averages and standard deviations of distributions? Use your TI. Run your L1, L2. This is exactly the same. I'm asking you to find the weighted average and the weighted standard deviation. Jessica, go ahead.
Of our roles or just
Use the theoretical. Use this theoretical. Your rolls are too noisy, and so are these right now, believe it or not. Yeah, use the perfect average. That way we can call it mu, and we can call it the population standard deviation. So take your time. I'm going to shut this guy down. I'm going to do it with you guys. Actually, I'm not going to shut it down. I'm just going to turn off the screen and turn this one. There we go. I'm going to play with you guys. And you'll notice as you type in the probabilities, you're going to get decimal equivalents of them. So that's 2.8%. So that's what 136 is. 136 is 2.8% of the time. That's all that's indicating. Then you've got 236, which is double that.